Hi everyone, thank you so much for joining us today. We have with us Kaiyu Yue, who is a PhD student at the University of Maryland. He will be presenting his paper Object Recognition as Next Token Prediction, which was published at CVPR 2024. Kaiyu is a third year PhD student at the University of Maryland, advised by Professor Tom Goldstein. So thank you so much for joining us today and taking out your time. I'll pass it over to you.
Thanks for inviting me to give this talk, and I very appreciate everyone to join this talk. And thanks very much. And can you see my screen?
Yes, we can see your screen.
Okay. So today's topic is object recognition. It's a super old topic, but it is new ways, new fashion as next token prediction. This paper is highlighted in the CVPR this year. The work is done during my summer internship at Meta last year. So my advisor is Tom Goldstein, and at Meta, my mentor is Bo-Chun Chen, Sirius Chen. And the topic is about object recognition. And given an image like this dog, we let the model predict the dog for this image. And we can have separate different kind of subtask for object recognition. And according to the single label prediction, we can have image classification. Imagine that we train a classifier on ImageNet, given a single image and output a single label. And then we also have a fine-grained categorization. And in this task, we don't want to just output the dog for this image. We also want to predict the Eskimo dog for this dog species. And according to the multi-label prediction, we have a conventional multi-class recognition task, and we predict multiple labels for image like dog, ball, road, and for this image. And in the industry, and they generally call this task as a tagging task or a tag annotation task because you want to put the tags for images to do the recognition system and in the recognition system. And there are some special recognition tasks like face recognition, and the object is a face. So for this dog face, and we can recognize it's who is the dog, and its name is a puppy. If the dog is a bad dog, we can use our security camera to use its face to track this dog. So in our work, we cover the above two tasks: a single label prediction or the multi-label prediction. It's a general purpose object recognition. Gives the image, we output the multiple labels for this image. And back to the object recognition, we have a concrete definition for it. It has two variables. The variable xv, v means the vision features. So it's a spatial image features. Imagine that we have the image forward the VGG or ResNet. We have spatial features. And with the dimension of HW by D, HW is a spatial size. And we usually, after that, we have an aggregation function and F, and like average polling or max polling to aggregate the spatial features into a single vector and 1 by D, and fit into the classifier. The classifier is another variable W here, and it represents the n classes or labels, the textual features. For example, on the ImageNet, we train classifier, the last linear layer has a dimension of n by D, n is 1000, right? So W is a classifier. So usually the pipeline is super simple. Given the image, like this cat, we have an encoder, extract out the spatial features, and aggregate into a single embedding. And along with it, there is another pipeline and for labels. Before doing the classification or training models or inference, we need to figure out what are labels, how many labels we have. And for example, on ImageNet, we will have 1000 labels. We will predefine this set and fit it into a function G. And that G can be a linear layer, like VGG or ResNet, initial or last linear layer to produce W. And if we want to train a clip, and we also need to predefine a set to fit into a text model or small language model to produce W. The W means that there's n candidate labels. We need to contrast with image features to perform the classification. And eventually we'll produce three or output labels with probabilities. For this case, the cat has a top one, highest probability, and compete with others, chair and mark around labels. So this is a general pipeline. So what's our motivation? And you may find in inference for the linear model, like we train VGG or ResNet, in inference, if we want to encounter a new labels, we have a new labels, we can do nothing to do with new labels, and right, and we can't change the W because it's fixed. And next, after the 2015, and we have a clip, and the clip has a dynamic W. We twist the input predefined gallery, and then extract out the corresponding weight W to as a new classifier during inference. But however, there's two drawbacks for the clips. The first one, if we don't look at the images, we never know what are the best labels for these images, right? And we want to produce a best label for this image. But the first step, we need to look at the images. This is a little weird. And the second thing, we want to let the clip covers all the vocabulary in this world, cover them as many labels as much as possible. And let's say we fit a dictionary into the clip, and we extract all the noun words from a dictionary, English dictionary, and use it as a predefined gallery to fit the clip. And it turns out there's two works. Also in our work, we found that when we append the query gallery larger and larger, the performance will be dramatically dropped. And there's two bars in this figure. And the blue one is we use a small gallery on the test set. It has accuracy. And if we append the gallery with more concrete labels or right labels, possible candidate, it will dramatically drop the performance. So this is this is another issue with clip. And why do we want to increase N? So when during my internship, my at Meta, my group is under the recommendation system, and they are the recommendation system team for Instagram or Facebook. Under Real, there's a in their product platform, there's a many new photos or images on the platform. So we want to recognize any object for those new images or new photos. We give them tags or labels. So yes, we want to increase N as large as possible. And hopefully this is experiment setting is open world recognition in the real world. So open world recognition means that it's incrementally when we encounter the new labels, we put in the new labels in the training and then produce a better models again over time. And there's a big difference with open vocabulary task. And the open vocabulary task is popular topic in the academia. And usually it has two label set. The one label set is called base label set. For example, it has 1,000 labels. And during the training, we only can train the model on this base label set. And there's another label set is called raw or novel label set. And during training, we can't not touch those novel labels, but we test the models on the novel labels to test the model's generalization ability on these new labels, and that are not say during the training. So these two tasks, we have a different purpose and a goal with the open vocabulary task. So in our setting, we want to let the classifier covers all the words in the world, because in the open vocabulary task, the novel labels kind of secret label set in the product. If we held out a secret label tag on the behind the product, we want to, for example, some users like Eskimo dogs, if we put the Eskimo dog in the secret label set behind the product, so we have a zero chance or less chances to recommend these Eskimo dogs to those kind of users. So we won't let this happen. So we want to let N covers all the words in the world. So this is our setting. So back to this pipeline again. And we have two goals. The first goal is N covers all the words in the world. So it's a super strong classifier W. And the other goal is in our pipeline, the image is the only input. It's different with the VGG resonance and different with the clip. We don't need to predefine the label gallery, only the input, the image. The image is only input. And after that, we output any labels are related to the image content. So this is our bigger goal. So intuitively, we can think about the language model because in the language output space, it can represent any words in the world. So eventually we want to let the N covers all the text tokens instead of the words or labels. So this is our first insight in this work. And then F will be language decoder. And after forward the image into the encoder, and we have features fit into the language decoder and language small model. And the W is the last out linear layer and out predict the next token for the image. The next token is label. So now you may tell this framework is literally the same with VLLMs, Lava, Blip, and I have a vision encoder, adapter, and then has a language model. And then we need to convince us to continue this topic. So why don't we need VLLMs? The first issue is too wordy. The output is paragraphs. It has many words. We need to post-processing to extract out the meaningful noun-words or noun-phrases from it. So sometimes, most of the time, we cannot get the enough valid predictions from it. Like if it outputted the 100 words in the paragraphs, it's usually always repeated some core concept in the paragraphs. So we can get many more labels from the small paragraphs. The other issue is that the VLM has a slow inference speed, and now they becomes larger and larger, and 7B, 8B, and 30B, 100B. And if you want to inference the image on the A100, it usually takes 2 to 3 seconds per image. So it's super slow. We don't want to run this image model behind the product to do the recognition system. And also the training data is different. For VLMs, they construct the triplets of image and the instruction or question and answer. And so it's a triplet input. We need to construct the instruction or questions and the QA pairs. But for the recognition task, we only need the pairs, the pair of image and the labels. So it's much simpler. So this the motivation convinces us continue this topic and we can do it better. So how to construct the language decoder? Usually, when we talk about the classifier, in our mind, it's a small, like VGG, ResNet, we have encoder, we have a compact last linear layer as a classifier, or like a clip. The clip has an encoder and it has a compact text model, only has several million parameters in there, not billion. So we also want to make the language decoder compact and small. And we have potential ways like distillation or pruning from larger to the smaller one. But in our way, we have a truncating way. This is more interesting. And truncating means that given llama, for example, llama 8B, it has 32 transformer blocks in it. So we keep the last output linear layer, and we keep the first several layers. For example, 1 transformer layers or 6 transformer layers. And for the intermediate transformer blocks or layers, we directly drop them. So eventually, our decoder is from llama 8B, but has a smaller size. It only has 6 or 7 layers in it. So it produces a flexible decoder size, less than B, half B, or 1B, 2B, anyway. And during our training object is simple. And you can see it's a token by token and using auto regression way. And for this image, we have, for example, we have three labels. So we tokenize as purple cat, and there is a special token between different labels, separator, and blanket, and sofa. And the first step is to do the token classification. And give the image, we have the feature, and it predicts the token. And if the label has multiple tokens, we multiply them together, just like how we train the language model. So it's a token by token. Here's the detail, is that for this training way is different with language model. The language model using transformer, it has a causal attention mask. It's a triangle way. It always selects the current token as condition on the previous tokens. This is because in the settings, the token has a strong relationship with the previous tokens. They have a strong semantic meaning. But in our case, the object recognition, the cat and the blanket, those two labels appears together. It's not because they have a strong relationship with each other. It's because this image has those two objects together at the same time. So the label should be independent to each other, but different labels should be conditional on the image tokens. So for this goal, we crafted the causal attention mask from a causal one to a non-causal one, and many small triangles in the attention mask. There's three columns in this attention mask. Three columns, blue columns, represent the image tokens. So all the label tokens can pretend to the image tokens, and the purple cat token, and then the green blanket token. The blanket token only see the image tokens, cannot see the cat tokens. So this is another difference in our model. So during our training is end-to-end training. We train the encoder, we train an adapter, we train a whole language decoder. So our training is only one-stage training. Is another difference with VLMs. Usually, if we want to train a blip or VLMs, we have a two-stage training. The first stage, we need to align the adapter to the encoder and the language model. And stage two, they will fine-tune the language model, and in our case, we only train once. And after finish training, and we start to prediction. And given the image, forward encoder is the same. And after we gather the first logits, and you really will have a sampling way like the language model. And we will use a greedy search or top P sampling or beam search. Both of these ways are sequential sampling method. It's token by token. It's in order. But we found that this is slow, and it's super slow. And it turns out our non-causal attention mask inspires us has another sampling way. You can imagine that after we first forwarding the image, we get the first batch of logits, and the next token can be any of correct labels. And it could be cat, or it could be blanket, or it could be sofa. But in this, in the first logit, it has a ranking order. In the top in the top K logits, it represents the tokens which has highest, which is highly related to the image content. So that's why we cut out the top K out of the total tokens as final top K labels candidate. And for example, we want to predict the top 10 tokens. We just cut out the 10 position and continue parallel sampling for the top K labels. If the label is finished, the sampling, and hit on the separator, it's finished, it's done. If the label is not finished, we continue to sample. So you can imagine this way is super fast because each single word only has one or two tokens. So it's super fast in the parallel manner. And one-shot sampling and has another benefit that is it the first time we can predict the top 100 labels for an image, because we can not predict the top 100 using VGG or ResNet. On the first clip, we can do, but it accuracy will drops. So in the autoregression frameworks, we can predict a larger scale, top 100, top 200 for every single image. And in this paper, we use raw image caption pairs from the 63 million Coco captions and SBU, and as our small training group. And we also have a larger training group from Lion and 100 million pairs. And notice that we also use raw image captions. That means we didn't use a human cleaning procedure or clean the labels, or we just use simple filters to filter out some noise and labels or characters from it. And our evaluation matrix is based on BERT score. And the BERT score has two parts. The first part is the record, and the other is precision. And the record is actually essentially is accuracy. For this finger, and we have three ground truth labels: cat, mug, and chair. And if the predictions there is a four and a cat, kitty, moggy, mug, and the cat has a best match with the cat, so it will contribute 100% accuracy to the metric. And the mug is the same for mug. And the chair, if say in our predictions, if there's no chair there, so it so it won't contribute to the accuracy. So in our reviewers, there's a reviewer, and at the first glance didn't get the record is accuracy. Imagine that we train a classifier on ImageNet. So the ground truth label, there's only one ground truth label for image. For example, the cat. And the prediction is 1,000. And its top one is a cat. So it literally is exactly the same with the ground truth label. So it will measure the top one accuracy. So that's literally the record in this formula. And because in our setting, open world recognition, and our prediction is cannot be exactly the same with cat, like a kitty or moggy. They are also represent the cat, but they have a slightly lower semantic similarity with cat. So it's still correct, but it contribute a little less accuracy to the metric. So the record is accuracy. Our validation set is 63 million validation set and Coco caption and open images. Yes, let's jump into the experiment. So this is a big table. We evaluate all the SOTA VLMs and also clip. And there's two rows for clip, and the green rows and the black row. And the green rows, we use a small gallery. If we evaluate the clip on the 63 million, so it's a predefined label gallery is only from 63 million. So we can say it has a little higher score than the black one. The black row means that we append we use a larger gallery. If we evaluate the clip on 63 million, the gallery is not only covers the it's not only from the 63 million, also from the Coco ImageNet, we gather a large gallery for it. So we can see from a gray one to the black one is a drop. The accuracy is a drop. And also the flamingo and the lava blip, this part. And yeah, ours has best accuracy and a recall, but a slightly lower precision. I will explain why we have a lower precision later. So this is a table. Oh, also imagine that our model is super small than those VLMs. We have only one parameters. We keep in our model, in our language decoder, we only have 6 transformer blocks in our decoder. So it is only 1B or nearly 2B. So small. So this is a PR curves. There's 2 columns in the PR curves. The second column has a normal shape in our mind. So we can first look at the second column. In the second column, we update the top K the K is the number of labels from the model. We're starting from top 1 prediction and the top 3, top 5, top 10. When we increase, the purple line is our model. And when we increase the top K, and then we can see the record is increased and the precision is dropped, and this is expected. And the blue line is clip. And then we can see the middle two lines, the green line and the gray line. And the green line is flamingo, and the gray line is instruction version of blip. And then we can see when we increase the K from 5 to 10, it saturates at this point. So that means it produces paragraphs. We cannot extract more than 5 words or labels from the paragraphs. So that's why it has higher precision than ours and clips, but it has a lower record in it. So this explains why we have a lower precision and they have a higher precision because they cannot produce enough number of labels in the for the image, but a clip and ours model can. So this ablation study is about the truncating method. And there's a different ways we can perform truncating on language model. Gives a llama, there are 32 blocks. Do we want to keep the first several blocks or do we want to keep the last several blocks? And in our experiment, we found that if we keep the first several blocks, it can produce a better performance. This is reasonable because the first several blocks is close to the input space. So the input space takes the image tokens as a software prompt. It is reasonable to produce a better performance. So in our model, we keep the first 6 blocks in our model. And this model and this ablation study is on the different language decoder sizes. And the first row is keeps the naive llama and the original llama, 32 blocks in our decoder. And then we continue to truncating, and we truncated the half, drop out the half transformer blocks, and get the 3B parameters, billion parameters, and we keep the first 6 layers, get the 2B parameters. And then we continue to drop, and we keep the 3, and we keep the only 1 transformer blocks in the decoder. We can see the accuracy is drop, but not dramatically way. So the truncating is promising and also can give us a flexible size of language decoder. So yeah. So this evaluation is from Rebuttal. And there's a reviewer ask us, if there is on the Hugging face, we have a tiny llama, or we have a small llama, llama 3B, why do we need a truncating? So we added this ablation study, and we use the llama 3B as our decoder, and train it using our training data set. And there's another decoder is we truncated from llama 2 from 7B to the nearly 3B. So it turns out the truncating can produce a better result. And we think about this. We think about the reason. The reason is that the 7B has a better input token embedding matrix and than 3B. So maybe this is the biggest reason why truncating can produce a better result. Yeah, this ablation is meaningful. And this table, and we compare our one-shot sampling, the parallel way sampling, with a sequential sampling method, like a greedy search using top 1 and a beam search. And we perform a 5-way beam search and a comparison. And the first point is that one-shot sampling can produce higher accuracy than those 2 sequential sampling ways. And the biggest benefit is that is the speed. And in this figure, and we use a different decoder size. And with our one-shot sampling, the green bar is using greedy search. We can see the speed is super fast. We can predict the top 100 labels for image in with 100 milliseconds per image. So we can, yeah. And after we almost done with our experiment, and OpenAI released their GPT-4 vision, and we need to compare with it because that's commercial VLLMs. So it turns out we still have a better accuracy on the benchmark COCO, and we found another interesting is that the GPT-4V is better than open source VLMs from the PR curves. Like I said before, and the flamingo or instruction blip, they will saturate at some point, because they cannot produce enough number of labels from model. And the GPT-4V can consistently produce a number of labels. It's following the instruction better and continue to drop. So this is an interesting point in this experiment. So we have another cross-validation. We treat the GPT-4V's output as a ground truth. So we benchmark all the models again and compare with us. So our has a better accuracy, so still have a lower precision. Okay, so the second, this part is a discussion in the paper, is covered in the paper. I will also have some discussion out of the paper. And in the paper, we had discussion several aspects, the wrong prediction, because when people heard that, oh, you are using language decoder, language model, is a hallucination there? Yes, the wrong hallucination is wrong prediction. Like just like before, we train classifier on ImageNet, wrong prediction exists. So the second point is less is more. In our training data, you may find we won't use CC12 milling. Yeah, we tried, but CC12 milling has lots of noise captions. We cannot extract out the meaningful non-words from it. So if we bring the CC12 milling in our training data, it will hurt the performance. So the caption quality matters. And how to define labels. We also try some many ways to construct our labels. In our final version, we only have a single word as our labels, like before, like a monster, cartoon, and every single word. But we have a better labels we can represent, like cute boy, green car, or cute running boy, poor green cars. They can bring more information and for us. But we failed on these two cases because we use a raw image caption caption dataset from a public version. So it's a super noise. We cannot filter out those concrete phrases from the noise captions. So we failed on those cases. Eventually, we keep the single word as our labels. And the evaluation is a model-based metric. You want to measure the similarity between different words and tell how correct are they. And we need to use a text embedding model to measure the semantic similarity. And this is also bring some bias or noise in our metric. It's not like the previously accuracy on the ImageNet, because we don't need to use a text embedding to measure semantic similarity, because we always know the output will exactly the same with ground truth label. So the semantic similarity will be always 1. And the final point is top one accuracy. Our model is not optimized for top one accuracy. We also have a table on the behind the paper, and we benchmark all the top one accuracy on the different fine-grained data set on the ImageNet. And then we are slightly higher than CLIP. But it turns out we think it's not meaningful, because nowadays, the single label cannot represent the image. And usually the image contains multiple objects. The top one is not important. And another big part is sampling method. There's 2 issues in the sampling ways. The first one is a repeating issue in the sequential sampling method, like greedy search, top P, beam search. And usually they happens in the small language model, and they repeat the words again and again, and and cannot produce a diverse output. So there's two ways to mitigate these issues. One is penalizing the logic of already sampled tokens, or you can train a larger and a larger LLMs, and makes the output diverse and more robust. And in our one shot sampling way, we don't have a repeating issue, but we have a competing issue. What is competing issue is that because we use logic as our top K candidate, what if the word labels correct? Both of them are correct, but they starting beginning with the same letters. For this image, we can produce animal and or art or alien. Both of them are beginning with A. If they competing with each other, and if they depend on the tokenizer, if the tokenizer tokens them with the same token, so we can only output one label of three. So this is called a competing issue. But however, and now the tokenizer in the language model is super redundant. It's like 32K. Now Llama 3, we have 100K tokens. So for this case, it's not a big problems, and we can still output the animal art aliens, those labels with the same beginning tokens. So these are result after accepted the CVPR, and when the new images from Twitter or our community, and I run my model and all those new images to test out um, how good the model is on those in the real world. We can see it can predict the Falcon here for the SpaceX rocket, and it can also predict the Sora. Oh, sorry, this one, Sora, can read the text in the image, because the ResNet or VGG cannot do this. Also, Clip also cannot do this, because if we don't look at this image, we don't know there is a Sora in there. So we never have a chance to put a Sora in the word in its predefined gallery for the clip. So the clip never predicts the Sora for this image, but our autoregression based recognizer can predict the Sora for it. So this is a benefit of using autoregression recognizer. And I want to discuss a little bit out of the paper. It's not covered in the paper. So if we train a classifier using autoregression-based frameworks, what problems still exist in the conventional times? Like we train a VGG or ResNet, we have long tail problems. So long tail problem still exist. For example, in this image, we can see there is a flower on the glass on the window, but in the output, there's no flowers. That means in our training data set, the images with flowers may be less than other labels. So we need to, when a flower is in the tail position, we need to append more images for flower to mine the flower, pop the flower in the top K position for the future. So the long tail problem still exists. And also, when we look at those two frameworks, the linear model or contrastive models against the autoregression models, and maybe in the industry, we have a different pipeline for using those two kind of frameworks. For the linear model or contrast model, first the step one is, what are our labels? How many labels we will have in our model, in our training? So we define the labels first, and then gather images for these labels and train models. And then when we deliver the model on the product, on the online, and then we found, oh no, we need new labels. So gather new labels, circle back to the step one, and gather images again. So loop this circle. And then for the autoregression models, the first step might not define the labels. We need to gather the images, high quality images, and our images for the product as much as possible, and then label every single image in a fine-grained manners, and label out every object in the image, used for the product purpose or any purpose, and then train the model. And then we deliver the model in the product. We found, oh, labels need to be mined because it's in the tail position. We need to let it pop out in the top K position. So we gather images again for this kind of labels and again. So you can see in the industry and academia, after this work, I feel there's a gap between the academia and industry. The academia is more like want to do the closed set recognition setting, whatever task is classification, open vocabulary task. Both of them essentially is a closed set recognition settings and finite labels. We need to long time to go from academia in the academia from the closed set recognition setting to the real open world recognition setting. And why? The first reason is that in our community, academia, we don't have a larger scale data set with fine-grained, detailed, dense multi-label for recognition task. We only have open images, also still have a finite label set. And this and like in this paper we did, in this paper, we use the captions. But however, in the community, we still don't have a larger scale data set with fine-grained, detailed, dense captions for images. So this is the two biggest reasons why we need a long time to go from the closed set recognition setting to the open world recognition setting. I still remember during my internship, and we don't have those two, we encounter those two issues, and I want to give up. So let's write a paper using 1,000 base classes and 500 novel classes to do open vocabulary task, but eventually don't pick this road to continue the auto-regression models. And compare with multi-label for recognition task, as a caption has another benefit that it's for general purpose, because we can, if we use dense captions for every images, and we can use training a captioning model and a training a classifier, like in this paper, and also using captions to construct the instructions or question answer pairs. So this kind of data set is for general purpose. So if you want to speed up the academia speed from the closed set recognition problem to the open open world recognition problems, we need this data set. So yes, this is advertisement. And in this week from our group, we have a super large fine-grained data set of dense image captions. It has 16 million dense image captions. We captions every single image with a long captions, and contains multiple informations and meaningful labels for every image. So yeah, yes, that's it. So thanks for joining this talk again. Really appreciate it.
Thank you so much for your time. Uh, if you have any questions, anyone can unmute and ask the question. I have a question. So, have you done any experiment on interpretability of this model, like how the output tokens kind of create a mask on input? So, have you done any
Oh,
study related to that?
yes, I have, but not in the slides. Um, during my part times, I check the attention maps in our language decoder, and we can look at this attention maps, like the rocket. You can see, and in some hat, it has a super clean attention mask in the language decoder. So this style is not clean as a Dino or something else, um, other models, but it's super clean for these images. So yes,
Or
also for this picture. It has a potential mask. Yes. The yeah,
Yeah,
yeah, beyond this, I didn't have a more interpret interpretation ablation studies on the model. Yeah, that's the only one. Hmm.
got I feel like it can easily be extended to the way it is designed, can easily be extended to multilingual aspects because if we train the language part with multilingual data set, it can extend to multiple languages. So I think it is a really cool thing in this regard.
Oh yes, yes, because our model is inherent the token embedding matrix from the language model. In our training, we always phrase input in token embedding matrix. So yes, if the language model can handle the multilingual task, and our model and it's the same. But yes, the most important is depending on the training data, you know.
I think there is some question in the chat as well.
Oh, sorry, can you repeat?
I think there is a question in chat as well. So did you use any image pre-processing like grayscale or inversion?
Um, sorry, I didn't catch.
Can you check the chat for this call in the
Catch the
bottom
what?
right corner? The chat for this call.
Sorry, check the what? Sorry, my
Uh,
bad hearing.
the chat for this call. There's a bottom in the bottom right corner. You can see a messages icon.
Oh, I see, I see. Yeah, yeah. Some plates. I'm not sure I catch up, but will tokenize the image. Does the image get any processing, like grading scales or emission, to reading the group of objects? Yeah. And SOYUZ, I don't know how to spell that word, pronounce that word. Yeah, it's yeah, so maybe it's a wrong prediction. Yeah. I think the feature recognition module might penetrate that issue. Yeah, yeah, I agree.
If you don't have any other question, I think we can conclude the session here.
Okay,
Yeah.
okay.
Thank you so much for your time.
Yeah, thanks, thanks very much again for inviting me to this talk. Appreciate it.
Take care, everyone. Bye.